In this video, I want to introduce some ideas of topology of the complex numbers. So topology basically just means we're going to talk about what does it mean for a set to be open. And topology in and of itself is a pretty deep topic where you can get pretty engrossed in it. And in fact, there's a whole semester-long course of topology that's offered in the department occasionally. You could do, you could study topology as much as you want. We're really only going to do just the briefest of introductions to topology and really just the stuff that's super relevant for us. And if we need more stuff at the time, we'll talk about it. But I just want to do a quick introduction of what does it mean to be an open set in the complex numbers. Before we even get to talking about open sets, I want to introduce the following terminology or definitions here. A circle of radius r centered at the complex number A is a set where this is going to be the set of all the complex numbers C, where the moduli of Z minus A is equal to R. Okay, so here A is a complex number, R is a real number, and R is in fact a non-negative real number. So you could say that as well. So R is real, but in particular, it's a non-negative real number. So this is the circle of radius R, nothing too mysterious. Okay, you have some point A, and then we're going to have a circle around A. It's not a great circle. Let's try again. So we're going to have a circle around A, and this circle is going to be of radius R. Okay, so that's what that set is. So if we were to blow it up a little bit, we would have radius R, okay, where A is the center. Okay, so there's a little nicer picture there. So that's the circle of radius R centered at A, and that's the notation for it. There's also the disk of radius R centered at A. And so this one's going to be a little bit tougher to draw, but this will be denoted D of AR. So this is the open disk of radius R centered at A. And what that means is that it's going to be all the complex numbers Z such that Z minus A is strictly less than R. Okay, so we do not include the circle itself. We're just talking about this disk. So here's our value A, and then we're talking about some disk of radius R, and then we don't include that circle itself. And so we're just going to talk about all those points there. So all those points inside the circle, not on the circumference of the circle, is the open disk of radius R. Okay, so this is the open disk of radius R. So open disk. I'll explain what I mean by open shortly. Centered at A. Okay. And that's the open disk of radius R. So now at this point, let's talk about what do I mean by open? What do I mean by, I'm avoiding certain words. So I said circumference before because I'm trying to avoid certain words. So let's get into some of the definitions here. So given a set G, so imagine that you have, we can just imagine that we have some set G, and maybe parts of G we include the edges of it, maybe parts of it we don't, and then all the points in here. Okay, so maybe that's what our set G looks like. It's just some random set in the complex plane. And so if we're thinking about different points of G or different points of the complex numbers, we say that a point, and I'm going to follow the book's kind of notation here, but a point A in G is an interior point of G if there exists some open disk, let's call it D A epsilon or DAR, if there exists some open disk that's a subset of G. Okay, so a point A is an interior point if you can find an open disk centered at A of some radius, and that disk stays inside G. So I just want to introduce this idea really quickly. I'm going to draw some pictures and then erase it as we go. You can pause the video, take screenshots if you like. But then I'll do one example at the end where we have all these definitions all together. So an interior point, what that means is it's a point like, say, over here. And the reason why it's an interior point is that I can find an open disk. Okay, so let's say this open disk. I can find an open disk so that that open disk stays inside G. So this red point here, A, that red point is an interior point because there's some open disk centered at that point A that stays inside G. If I were to pick a point here, then it doesn't matter how small of an open disk we're talking about. That point's not in the interior of G because that's that open disk. It doesn't matter what open disk it is. If you're right on that edge of that border, some of the disk will be outside G and some will be inside G. Okay, so those are not interior points. Interior points are like this one, so that there's some open disk centered at that point that stays inside G. Okay, so that's called an interior point. All right, that other topic that we were talking about, if we say a point B, so a point B is a boundary point of G if every open disk, I can't spell disk, centered at B contains points in G and contains points not in G. Okay, so those points are called boundary points. So let me just zoom into the picture that we had before. And inadvertently, this second example that we were talking about, that's a boundary point because no matter how big your open disk is, I don't care if it's huge, I don't care if it's tiny, it's going to have some points. There's going to be some points in that disk that are going to be in the set G and some points that are outside the set G. I also want to emphasize, so let's call this point B, and this was the point A. I also want to emphasize that if I were to pick some point over here, that's also on the boundary of G. Even though that point itself is not in G, that point is on the boundary of G. Because again, any open circle centered at that point will contain points in G and points not in G. So that's again a point on the boundary. So just notice that that's why it's okay for a point B to be a boundary point if it's just some generic complex number. It doesn't necessarily have to be in G, but interior points have to be in G. There's no wiggle room there. Okay, so point B is a boundary point if every open disk centered at B contains points in G and points not in G. Let's keep going. I'm going to go slightly out of order of the book, but a point D. Okay, so point D in G is an isolated point if there is some open disk centered at D containing whose only point in G is D itself. So what we mean by that, and I'll need a new picture here, But let's say that we have some set. So here's G, and G also contains this point. Okay, that's an isolated point because what we can do is we can find some open disk centered at that point D. Okay, so this is the point D. But there's some open disk, and the only point in G that's inside that open disk is the point D itself. Okay, so that's called an isolated point. Okay, so notice that G contains that point D.